Okay, ELE112, welcome to section chapter 8-4, Superposition Theorem. If you think I'm speed reading through this, it's because there's 6 slides here and a bunch of stuff to talk about. What you will find in this chapter is that the circuits are simpler. They're complicated if you don't follow the recipes that I've set forward, and I'm going to go through the steps, but man, I wish there was just an easy way to wave a magic wand and get this done. Superposition theorem is complicated, even though the circuits will be really watered down. It's complicated because there are 2 DC circuit supplies, sometimes 3, although we generally don't get into that, but there could be 3 or 4 power supplies running a circuit. There could be a power supply and a current source, making it, complicated. And we have to know, as we solve the circuits, we never solve the circuits with all the power supplies in the circuit at the same time. We have to remove the excess power supplies, which means in the case of voltage sources, we're going to take voltage sources and they're going to be shorted like this. Extra voltage sources. Current sources, on the other hand, are going to be opened. So if you could think of a circuit with 2 supplies, one of the 2 supplies during analysis gets shorted if it's a power supply, or opened if it's a current source, and so on. So we'll be going through some of that material as we go through this introductory lesson, 6 slides long. There is a simple introductory problem, and then we'll work a couple of more in future chapters of chapter 8-4 so that you can kind of get the hang of it and handle some of your homework. So, as in terms of steps, we have to continue to work this particular section with the assumption that current always flows from the positive. Well, we're going to have to talk about that when we get there. We're going to have to draw arrows. We're going to have to use colored markers, colored pencils of some sort, like I did on the last page, so that we don't have our heads exploding when we start to build equations and solve circuits. So, step 3, building current equations from step 2 drawings. Our goal, if I didn't say it, I'm going to say it now. Our goal will always be in section 8-4 to find currents in each component, total currents, by isolating the multiple power supplies one at a time and finding out what does each supply contribute. Once we've done that, we can algebraically add those currents. They will either add or they will subtract, depending on the orientation of the supply, producing a total current. That total current will let us do V equals IR. In other words, V equals I, the current that we found, and the R is the component. And we'll be able to figure out all the currents and all the voltages this way. Bullet number 4. Because there's more than one power supply, you might have to solve the same circuit slightly different from each power supply's perspective and resolve. You'll take batteries and short them. You'll take current sources and open them. And then number 5, we'll be able to calculate very, very easily all the voltages across the resistors, assuming the first 4 steps were done right. First thing to realize, if you're watching this video, you're starting 8-4. If you sleep on this, bad news. There are very few homework problems in 8-4. They take twice as much work because of the 2 batteries or more situation. So if you snooze, you lose. Fair warning, right? All right, let's side of the battery. Here's a sample picture showing where we're heading in a few minutes. and you'll see that I've drawn some red and black arrows from each of the power supplies, and power supply 1 on the left, V1, the current in the red line goes up and to the right, while supply 2, known as V2, goes up and to the left. And what that does is it creates currents from each supply that sometimes go in the same direction and sometimes they go in opposite directions. In this particular circuit, you can see down at the bottom there where I've drawn resistor 1, resistor 2, right here, you can see that the currents are going in two different directions. To the next slide. Here is our simple circuit, and short of making it one resistor in size, I gave you two resistors. This looks like a big party, a big series circuit. I want you to notice that the two supplies are not truthfully in series with each other. So you can't just take the 10 and the 5 and make it 15. You can't just take the 10 and the 5 and make it 5 because they are isolated by the resistors. So what we're going to have to do is take one supply away by opening or shorting it and solve that circuit. Now that's not a whopping circuit. That's a real basic chapter 5 circuit. We'll go in and solve it, and then we'll take the other power supply and wipe it away and bring the second supply back and go solve currents. So this is the process that we're going to take, and of course it's going to take twice as long, and this first problem is going to take forever because I have to teach you exactly the technique. Without the technique, it gets really nerve-wracking. So, step number 1 said, assume the currents flow from the positive side of the battery, and I have taken the red and black colors that I suggest you use, different colors for different supplies. And the red path takes you out the positive side of the battery and around clockwise, while the black side takes you counterclockwise. Now, could you work these problems going out of the negative side? Sure you could. You'll have enough challenge doing it out of the positive side. Why the heck would you mix techniques? Fair warning, you should not go out of the negative side of any source. You should go out of the positive side and do things the same way every time. Every time. Keep it simple. Now, second assumption. Ask yourself, how many power supplies are there? Answer. Did you figure it out? There are 2. So, to keep it simple, you have to, as part of your analysis, have techniques that you repeat over and over that you don't have to wonder if you're doing the right thing. So I'm going to say keep it simple. Not only draw the arrows out of the positive side of your sources, always, what I mean is always assume that V1 power supply current source runs most of the circuit. Assume that V1, even in this case, assume that V1, which happens to be 10 volts, it's bigger than the 5 on the other side, is larger. And we'll find out why in a future page here in this video. We will potentially make the wrong choice. We'll assume V1 is bigger, but sometimes V2 is bigger, and we'll be able to go pick up the pieces and make some corrections in some future circuits. So bear with me, keep it simple. always assume supply 1. You know, the supplies are all going to be labeled V1, V2, V3, V4, V5. It's pretty easy to pick V1 as the largest. Do not be swayed by the numbers. So if V1 in this particular circuit was only 2 volts, I would still assume that V1 was the larger of the two supplies. And it will become clear as we work through this why we're doing this. Okay, let's see. Notice that resistor 1 and resistor 2 have been redrawn at the bottom of this page, and you can see that I have taken the time to draw the arrows in the directions that the actual current is flowing, and you'll notice that I have circled in black the orientation of the voltage drop. If current's going from left to right, it's dropping plus to minus. Now, the reason why resistor 1 is plus to minus is I've assumed the red line is bigger. The red line current is the larger of the two. It may not be true at the end, but right now it is. And if you look at resistor 2 over here, I've done the same thing. Red is going from right to left, and I've assumed that it is exactly the same way. So plus to minus from right to left in this particular case. The currents apparently counter each other. In other words, they subtract. You can see it right there in the drawing. Sometimes in future circuits, they'll go in the same direction, which means the currents will grow. We will always assume, as I said before, that V1 is greater than V2. Now, the video is getting kind of long, so I'm going to try and, hopefully without screwing this up, try to save this video for future use. Okay, here we go. Continuing on here. Then we're going to get back to that circuit. I'm going to be looking to calculate the current here in this blue resistor and the current here in this blue resistor, and I need to find out how much current this supply pumps through R1 and R2. And I need to find out how much current this supply pumps through our next page. Here's the spot where we learn to combine the current equations. We got to solve the circuits 2 times. And what I've done is I've gone through and I've looked at the 2 components. There are only 2 resistors. You see right here, resistor 1 and resistor 2. And I have said that the current in R1, the total current, is the sum of the current in R1 from the first supply minus the current in the same resistor as a result of the second supply. That makes sense. That says that if the red line's bigger than the black line on the last page, which is current that is larger in IR1V1 than in IR1V2 here, and they're going to subtract. Same thing for resistor 2 below. If you take a look at IR2 total, I've written an equation which is equal to IR2, the result of source 1, minus IR2, the result of source 2. This always assumes, as you can see the negative sign that I've drawn in there, the subtraction basically says that whatever I have on the left is assumed to be larger than what I have on the right. And I could be wrong at the end. When we get to a circuit that does that, we'll figure out how this happens. So, to summarize, I'm going to 1 and R2. And so that's what I'm after. That's what these 4 quantities are right here moving forward. So as I solve these things, what I'm going to do is I'm going to come back to this equation right here. okay? And I'm going to X out and fill in the actual current values and get the totals, which are shown in blue here, okay? So that's our goal. We needed up in this region right here. We just solved. Here we are. Step 1, page 4, for the first circuit. We took the power supply and we put a short in for V2. Now we need to go get the currents here and here. Well, how hard could this possibly be? It's a series circuit with 2 resistors and a 10-volt battery. So the total resistance becomes 3K. The total current is just Ohm's law, 1.33 milliamps. Well, that's the total current in the circuit, which happens to be the current in I2, which happens to be the current in I1. And you can see that the dominoes are already falling because I just figured out 2 of the quantities that I need in this circuit. Wow, blow me away. That was fast. You're done with part 1. Now we load up part 2, and you'll notice that we short the second supply, and we're faced with the same problem, basically. It's a simple series circuit that if we calculated here, we get 3K. 1K plus 2K is 3K, and the current is different than up here because we only have a 5-volt battery. So what we found was the total current. What we found was the current in the first resistor, and what we found was the current in the second resistor, and that is right here. Do you know that the 2 items in red, here and here, are exactly what all 4 of those quantities? Most of the work is done. Moving on to page 5. I've taken the liberty of dropping the values from the last page into the current equations we had at the beginning of the problem. You see they're sitting right here. These are the 4 currents that we just solved on the last page. If you plug them into my current formulas that I developed based on the direction of the arrows, well then, if that was the case, these are the currents that are flowing in that circuit in one direction or the other. Now, since both of those answers in green came out positive, that means our assumption that the current was flowing out of the positive side of the battery was absolutely 110% correct. Now, I don't want you to be misled. I don't want you to think that every time you work these problems that you're going to get the same number here in black, because that's not going to happen. It's very rare that it happens. We have just a bloody simple series circuit, and luck of the draw made that happen. So let's take a look. Again, here is the summary of everything so that you can look at it. You see, we have a current here of 1.66 milliamps for both resistors here. One of them is flowing from left to right. The other one's flowing from right to left. And we've got 2 batteries in there. So all we have to do now is, since we know that they are 1.66 milliamps, is go do Ohm's law right here. Resistor 1 and resistor 2, they both get 1.66 milliamps times the resistance, and look what you get. 3.33 volts for V2 for resistor 2, and you get 1.66 volts for V1 resistor 1. Let me ask you this. A series circuit with a 1K and a 2K, who gets more voltage? The 2K. By how much? Twice as much. Did we get twice as much? The answer is yes. The last slide. Yes, we are at the last slide. We've been moving aggressively. Let's prove it. Just out of curiosity, if you don't have an answer key like you do for your homework, if I wanted to check this circuit, I now know the voltages, 3.33 and 1.66 up here in the green circles. If I follow the red line and I start by moving through this source, and I pick that up and I do a Kirchhoff's voltage law. Kirchhoff says that if I go around this loop and follow that red line, the sum of all those voltages, if you know the orientation correctly, equals 0. So we're going to pick up minus. Now, the reason why we pick up minus is follow the blue line. The first thing we see in this power supply is a negative. So we pick up a minus 10 here. We loop around and we pick up a positive right here, a positive 1.66. And we add a positive 5 as we move through this supply here. And as we go through this resistor, we pick up another positive 3.33. Guess what happens when you add them up? It worked. Stay tuned for more videos on superposition.